Okay, welcome to Chapter 5. This is the second of the electricity topics, and it's diving down more into the atomic level. So it's starting to look inside everything that's inside your circuits rather than looking at the circuit itself. So we're going to move beyond the Kirchhoff's rules, which everything's based upon, and we're going to look at the foundations of what causes the link between them. In other words, resistance. So we're going to start with resistivity, which tells us not about how much your resistor is doing, but actually what it's made of. So we're going to look inside that section to kind of take it round. If we look at the chapter to start with, again, we're going to bring in some other ideas, which is the whole cause of resistance, etc., the whole reason for it, about delivering power and bringing that link in, and how different properties behave in different ways. So we're going to look at resistivity in a metal, and then we're going to compare it to other materials to see where it goes from there. Excuse me while I just adjust this. There we go. So inside, we're going to start off with the basics. This is mainly about the experiment, so do the experiment first and we can pick up all the little ideas from that. So we're going to start off with the idea of what we mean between resistance and resistivity. So resistance of metal wires is caused by, again back to basics, free electrons colliding with the ions of the material. Okay, and it's this bit that matters. So it's the material and the ions. So if we change the shape, the size, the conditions of what's going on in it, then we will find that everything changes around the ions and the collisions. So when we're talking about resistance, we have a certain number of collisions going on. What we're actually talking about with resistivity is about the probability of collisions, and that depends on lots of factors. Okay, so free electrons collide with the structure itself. Resistivity is the likelihood of collisions. Now put that in brackets, you won't need that as description, but it's about the material causing it. So what the variables are is pretty obvious. You know, if you have a longer wire, as you studied at GCSE, then you're going to have a greater resistance. Logic? Why? Well, a longer wire means that you have a longer lattice of material, and so that's going to go to greater number of collisions. Okay, so greater probability of those collisions. Number of collisions a second is what causes resistance, but this idea of having more chances to collide is going to be a bigger resistance overall. The area, a little bit more confusing perhaps, because again you've got a bigger lattice, you've got more in your lattice, you have more ions in the way, but effectively with an area you've got a larger cross-sectional area, which means just not just more ions, but actually more gaps within the ions. So that leads to more pathways between the ions. Okay, so there's more chances of getting through with less collisions than there is with a longer wire. And then temperature means has a big effect as well. It does not affect the material, but it affects how the material behaves. So with temperature, you're just going to have, we're going with, again, larger, so higher temperature has the greatest effect. Okay, this is 2 lines of writing here, so just be a little bit tight with it. Gives ions more kinetic energy. And so because of that, that leads to the fact that you're going to have bigger vibrations. So let's go with larger vibrations. Vibrational energy within the lattice then leads to more frequent collisions. So we looked at this with the idea within a bulb, and kind of makes more sense because that's just a length of wire in a filament bulb. However, it's this idea that the material is what's changing. You're not actually changing the resistance itself, you're changing what's happening at this atomic level. Okay, so subtle difference you may think, but it's not about that. It's kind of thinking away from the object, what we've made from the material, more about the material. So the equation that links in with this is fairly logically obvious if you look at the variables above. The resistance of a material depends on what it's made of, so that's its resistivity. So rho, again, unfortunately, same symbol as density, can be thought in a similar way, but it's not the same thing. It's not a physical property of the material, it's actually its opposition to material itself. So resistance of a length of material can be calculated from that. So resistivity of the material I keep rephrasing that, re-establishing that, because people don't pick it up in their head. So resistance is of the bulb, motor, whatever, what it's made of has resistivity. So just keep that in your head. So that's material. L, again, longer wire. That's going to make more collisions, as we said up there. So it is directly proportional. So is length of material. Again, it's always really worth putting that in with definitions. This is almost a definition here. So resistance is these components. And the other one is area. So again, doubling the area, not diameter, doubling the cross-sectional area is what's going to make the difference to resistance. Sorry, what am I doing? Sectional area. Okay. Again, if you are to use this as a definition, as in you can almost describe this, resistivity is resistance of a material where equation rho is this, L is that, A is this. You do need to make clear it is not the outside of the wire, it is what the wire sees as the electrons flow towards it. So it's the end of the end area of the wire if it is a wire. Now, how does the other bit come in? Well, it doesn't affect this. Temperature has no effect on this directly, but it's on the, so it doesn't have a change on the structure, but it does change how that behaves. So this idea of not that value, obviously, but the movement and behavior of the particles. There's a little bit in link in here. So let's just have a pick up on that. And again, some people do it as resistance, but we'll do it as the proper thing. And I will point out that this is an extra beyond our course, but resistivity depends on the original resistivity. Okay, so put that in, original value. Okay, a bit low, we use quite a lot in things. And we're going to add on to that a multiplying factor, and it's about the temperature change. So what I'm going to do is I'm going to split that up. So rho plus a multiplying factor of rho naught. Sorry, rho naught plus a multiplying factor of rho naught. What I'll do is I'll multiply it out into brackets. So we'll have a multiplying factor, and that multiplying factor is all dependent on its temperature, obviously, but it's the temperature above the temperature at the original value. Okay, so it's temperature rise from when this value is taken. And this multiplying factor, like a lot of things, it's all about a ratio. So if we were to double the temperature, then what you'd find is that value would be double that one. Okay, using that kind of idea. So it's a coefficient. That's what that means. That idea of ratio is the temperature coefficient. And you'll see that word quite a lot in science. Coefficient just means multiplying factor. A lot of European countries use that word instead of ratio. So it's the same idea as a ratio. Now, having done the practical, or if you're about to do the practical, then you can kind of use this as background. If we want to find out about this value here, which is going to be the aim of our practical, then we will need to change factors. Now, it's quite easy to change the length, so that's what we'll do in the experiment, but that length will affect the resistance, and we cannot measure the resistance, so we would need to measure voltage and current and use Ohm's law to find resistance. Now, if we change the area, we could double the wire and put two side by side, then that would be doubling the wire. It just means that we have a smaller number of changes we can do, so a smaller set of readings. So length is easier to adjust continuously, have a whole range of values, whereas area tends to be more discrete. You know, we double the area, triple the area, quadruple the area. So we'll change the length, but the crucial bit is this is also affected by that changing due to temperature. So crucially, when you're doing the experiment, if you want any hope of getting an accurate value, then you'll need to make sure the temperature does not change. Okay, and we can do that in various ways, but crucially, if you think about it, temperature, heating, ohmic heating, depends mainly on current flowing through your length. So when we're thinking about that, actually, we want to just keep the same current, because if we have the same low current, we'll have really low heating, and it should be very predictable. Okay, so that's where our experiment goes. It's to try to measure resistivity. It's a classic experiment as such. And with like a lot of A-level physics experiments, it involves a piece of wire. So we're going to use a length of wire, and the similarity in terms of how to do accurate measurements that we'll spend some time on afterwards analysing is based on the same principles as it is for Young's modulus, for example, or the standing wave in a string or a wire. Again, it all depends on the same kind of measurement values. So all of that's in there, in the pack where it says there. However, let's bring them together. Okay, now you have made some notes if you've done the practical already. We'll have gone through this in lesson and tried to identify where those sources of errors are. Excuse me, let's get that square. But the crucial bits is spotting the main points there. So what could we do? We looked, as I say, done the calculations, finding about how to affect these results here. Okay, but actually, if we think about what we can do with these results beforehand, then you'll always get better results after. So what could we do? Think about the length. Okay, if we have a longer wire, that should give us better results. Why? That comes from a smaller percentage uncertainty for the length. Okay, so let's just put in L, whatever that length is. But it does mean, so I'll put in brackets, but it does mean the current's smaller because there'll be more resistance. So you may find, may increase, and we'll just use percentage uncertainty, shorten it, in current. Okay, so your current values might be so small that if they're small on your measuring instrument, if they're small on your ammeter or milliammeter, microammeter, whatever, if they're low down on the scale, you'll find you'll have a bigger measurement uncertainty in there. So you don't want it too small, so you don't want that too big. Okay, but long lengths will always work better. Okay, we can have a thicker wire. Okay, so a thicker wire will actually reduce your resistance more. So that gives you, again, a smaller, I should say, there should be smaller uncertainty in that. It will give us a smaller percentage uncertainty in A, but it'll also mean that you end up having more current. So A and current I. But the problem is, you might find the change is not as measurable, you won't get much difference between the readings, and more importantly, but that gives you more current. And so if you get more current, you're going to get more heating. Okay, so perhaps a thinner wire is better, but it will mean a larger uncertainty in your measurements for the diameter of the wire. Okay, so overall, what that means is, or what that leads us to, is a short thick wire, or short fat wire, has smaller uncertainty, has smaller percentage uncertainty, but as he said there, it brings in these other factors. So the measurements will be better. Okay, but it causes more external factors. Well, same external factors, but a bigger effect of external factors. Let's put in effect. In other words, it actually makes your experiment less valid. Why? Less of a fair test. So it's always this trade-off, and it's trying to think about this. So validity is the obvious main thing that you're trying to achieve with your experiment. So you want it to be as fair as possible. You want the current to be smallish. There's ways around it. So for example, you could put a little switch in so that you make sure that it's only on for a short time so it doesn't heat up. So that will reduce this effect. But bottom line is, if you find that your experiment is giving you a graph that doesn't fit that pattern, in other words, it's not a straight line, then you know the validity of your experiment is pretty low. Okay, so good valid data, good valid final result, you want a nice straight line graph, which does mean you need to control these external factors, even if it makes your measurement uncertainty worse, i.e. bigger. Okay, so kind of same ideas as said with stretching a wire. A longer wire and a thinner wire will actually be harder to measure, but it will give you better results. It will give you a bigger change in the stretch of length of a wire. So very, very similar to Young's modulus. Okay guys, that was that section.